Hi people, welcome to eTalks by International Erguvan Art Academy. I'm Mayam and I'll be your host for today. Erguvan is an activist group planning and implementing various projects, educational programs, seminars, and productions for the past 20 years. Based on the radical idea that art will save the world, Erguvan aims to spread awareness of how important artistic expression is both to individuals and society at large. Our events cover a range of topics including culture and art presentations, seminars, symposiums, workshops on different fields of art, artist gatherings, exhibitions, concerts, shows, and science and culture field trips. eTalks is our talk show where we are joined by experts in the fields of science, culture, and arts. Dr. Z is an Israeli-American mathematician who has made important contributions to the fields of hypergeometric summation and Q-series. He was also the first to prove the elusive result in combinatorial theory, known as the alternating sign matrix conjecture, as well as a number of related propositions. He was a co-recipient of the 1998 Steele Prize of the American Mathematical Society for his research on hypergeometric summation. And our moderator today will be Nuray Kutlu, who is a mathematics and computer science major at Rutgers University and is my friend and roommate for 2 years. And they will have a conversation on experimental mathematics today. So welcome, Dr. Z and Nuray.
Thank you, Mayam, for the introduction. Okay, so Dr. Z, I'm actually a very newborn experimental mathematician, I would say. So I have a lot I want to discuss, even though I'm definitely an experimental mathematician. I have some questions and observations as well.
So you took my class and you're doing very, very amazing project.
That's true. Maybe I'm a toddler then. Maybe I'm not a newborn. But I took Dr. Z's class, experimental mathematics, for one semester, and I also audited it for a second semester. And now I'm doing research with Dr. Z, experimental research. So I guess I can get started unless you want to start off with anything, Dr. Z.
Yeah, first I want to say how much I love Turkey. It's one of my favorite countries. And I want to drop a name that I already told Nuray, but I want to share it with other people. When I was a young PhD, right after my PhD, I had the good luck to visit Ankara, the Middle East Technical University. And I was lucky enough to meet a very nice, at the time, old gentleman. It turns out at the time he was much younger than I am now, but he seemed like a grand old man, very nice and friendly. And I knew that he was a very distinguished mathematician. But in my country, in Israel, or United States, when you have money, bill, you have in the United States, you have Jefferson, you have Washington, Lincoln, you have former politicians, presidents, statesmen. You don't have scientists in Israel either. The only one who ever made it to be money is Albert Einstein, I think. And otherwise, it's either politicians, statesmen. So when I went to Turkey a few years ago and I got some money, I was really, really so happy to see that this old gentleman at the time, they were so friendly to me and made me a cup of tea and we discussed some mathematics for half an hour. Happened to be in the 10 lira. Right here, you see it? Yeah, 10 lira bill. And this is Kait Arf, who was a really distinguished algebraist. But still, I really admire Turkey that he puts a mathematician into the money. They have a great respect for mathematics and science and art in general, unlike most countries in which usually only politicians and at best artists, but not scientists. Anyway, that's my name dropping. Thank you. Go ahead.
Yeah, I actually have a 10 lira with me right now, the one that you gave me on our
Yeah,
field trip last year. So I was
yeah,
gonna show that if you didn't have one.
yeah.
Yeah. But yeah, I think that's really cool too. I hope that the US has mathematicians on their money sometime soon. Maybe they can put you on the dollar bill, Dr. Z.
Maybe.
Um, Okay, so I guess we're going to talk about experimental math today. And if we're going to talk about experimental math, we can't not talk about the fact that experimental math is so overlooked. And we have, a lot of tools on our hands that if experimental math was more widely accepted in the math world, we would be able to, improve a lot more than we can right now. I mean, most people think that math is in the background of computers, but we can also make computers in the background of math and use them as a tool rather than just the other way around. Because I think most people think that if you want to use computers for math, it has to be to draw figures or, write papers online or something, but they can also be used as a sort of telescope or like a technology that we can use to research math. So I think though that like naturally because computers are becoming more widespread now and many people are becoming, tech experts that the math world will come along and computers will be used more and experimental math would be more widely accepted. But I guess this is my question and something that I've been trying to um, come to terms with myself. Technology or empirical evidence is very accepted in other fields like science fields. I mean, maybe
Yeah.
there's some sort of like rigorous proofs in those fields as well. For example, in chemistry, I don't know. But I think it's much more accepted in biology to look through a telescope and see something and say that that thing is that thing. While in math, you need a very rigorous proof to show that that thing is true. But I wanted to discuss this thing with you, Dr. Z. So imagine a world that has incorporated experimental mathematics. So how,
Yeah, there will be in probably 50 years, maybe sooner,
yeah, I think so too. I think it's,
completely. No, right now it's already a growing thing, but it's still
yeah.
a fringe part of mathematics. Yeah, go ahead.
No, yeah, you're right. I agree with that. It's a lot more than it used to be, I believe, although I wasn't really alive back then. But so, I was just gonna say we can't just blindly accept every form of, evidence as evidence, even if it's, empirically proved up to a very large number. We can't just blindly accept it. There has to be some sort of, guideline to go about that because, there are big numbers that some conjectures work for, but some conjectures don't work for very big numbers. So what is the kind of what do you think? How can we have a guideline for that?
Yeah, that's a very good question and uh, objection. Indeed, uh, also in science, uh, my dream, the mathematics will be uh, more like physics and chemistry, will be an empirical science because I have, if you look at complexity theory, it's, you know that as an analogy with computer science, most problems are intractable. There's no way that we ever be able, for example, to solve, to have an arbitrary graph with 10,000 vertices and uh, and maybe 100,000 edges and decide whether you can color it with three colors. This is such an elementary question you can explain to a 5-year-old. So we know, assuming that, like most people, uh, reasonable people believe that so-called NP hard problems are intractable, then we know that we have to live with this, that most things are not completely provable. So that's an
Yeah.
analogy. So conceptually, the coloring is a conceptually trivial problem. in an ideal world, if we had a big enough computer, we can just do it by brute force. So it's only an analogy. So analogy, so most of mathematics has been done so far. Humans did it, and no offense to humans, still humans are very limited. So even these big theorems, for example, a famous theorem called Fermat's theorem that famously Andrew Wiles proved it from the grand scheme of things. In other words, in the eyes of God, is in some sense trivial. Most of the things we would impossible to prove completely rigorous. So all those what we did so far is very nice, but it's just like playing Sudoku, something a human can do. But if you take a 10,000 by 10,000 random Sudoku, no human or even computer can do it. So we have to learn to come to grips with the fact that mathematics is about mathematical facts. But the tradition so far was that the sine qua non was you need a rigorous proof, and everything that was not rigorously proved was derogatorily called a conjecture. But you are right that we need some criteria. Just checking something for 100,000 cases is not enough. There are so many examples that obviously when you check something even for 1,000,000 cases, then it's wrong the next one. So we need to develop, and that's part of the future of mathematics, criteria for reliability of I call it semi-rigorous mathematics and non-rigorous mathematics. In 1993, I wrote a controversial article that is still controversial called Truth for a Price, Tomorrow's Semi-Rigorous Mathematical Culture, in which I said that we have to come to grips that some results will never be able to prove with 100% certainty. But many results, you can quantify it and say this is true with probability 99.99999 with maybe 20 nines after. It's so sure, it's practically sure. And we have to accept this if you want to advance mathematical knowledge. If you only be stuck with things that are completely provable, we won't go as far as we can.
Yeah, I think that makes perfect sense. And for some reason, we accept that for other disciplines, but we can't for math, which is interesting. But I was actually thinking about, maybe drawing a bridge between rigorous and empirical proofs where they like kind of have like a partnership. And maybe I told you, but I read your paper on toads and frogs last semester, the one with
Thank you. Yeah.
Yeah, and there you guys used empirical evidence and computers to conjecture some things, and then with the conjectures that you made through empirical evidence, you proved again using the help of computers. So although you did form a fully rigorous proof, you did that through the help of computers. So maybe at least for now, even though obviously it's still important to have empirical, or at least like kind of empirical proofs of things, you can also use computers to help conjecture and help prove rigorously as well.
Of course. I love proving whenever possible.
Yeah.
Of course, ideally, it's still nice to prove. For me, it's fun to prove things that they are beyond the scope of humans, but computers can prove. And quite a few of my papers, including the frogs and toads, with my former student, Tana Pitanonda, that, of course, whenever possible, it's nice to have a full proof. But sometimes you can have a proof plan that shows if you have a big enough computer, either in practice or in theory, you will be able to prove it. And then you have good indications that by taking random sample, that is provable. I call this kind of proofs semi-rigorous. So we lucked out. In this case, it was fully rigorous. But it's very possible to have other cases where, in principle, granted that we have a computer big enough, as big as the universe, it's possible to do it. And sometimes it's possible to do it in practice, but it'd be so costly. So it'd be a waste of money to have this obsession with absolute truth if you can get almost truth with a fraction of the price. But you are right. Whenever possible, by all means, it's nice to have a rigorous proof, and it's nice to have computers find a rigorous proof. But if it doesn't work out, then you should not be too obsessed and be happy with a semi-rigorous proof, unless and only have a rigorous proof if your budget allows it. Don't waste the taxpayers or your own money on things like this.
Right. Yeah. Yeah. I mean, I think these rigorous proofs that are created with the help of computers can draw a nice bridge into experimental mathematics, at least maybe open people's minds a little more to accept, semi-rigorous proofs.
Yes, I agree.
Yeah, rigorous proofs.
Well put.
Yeah. I also think that, sometimes you have a rigorous proof, but it's very, very long, like 20 pages long or something. And, sometimes people can make mistakes, with the rigorous proof, but computers can, find things up to a very, very high, amount. And I guess my question is, do you think that, people writing rigorous proofs that are very long, that could possibly have mistakes that nobody catches on to, can be even more faulty than semi-rigorous proofs that have been proven using
By all means, humans are very imperfect, and I'm sure that many proofs. You always have. I mean, you talk about human-generated proofs. Oh, I'm sure that many, possibly most, papers in the literature generated by humans have some errors. Most of them not important, hopefully, but and you have, in the case of very famous theorems, people go over it carefully and sometimes point out mistakes, and then they have to publish a correction or a retraction. But most papers, nobody has a patience to read, and so most papers, probably there's a lot of undetected errors by humanly generated proofs.
Yeah, like I remember when I was taking your graph theory class a bunch of semesters ago, you talked about the four color theorems proof and how it's really long, and there kept being errors in the rigorous proof, but the empirical proof was really simple. So yeah, I think like human errors and people not having the patience to go through a proof and things like that, that can even cause more issues later than just having an empirical proof, which is maybe semi-rigorous. So I think.
But let me interrupt with my pet peeve. A very fashionable area now is computer logic and making so-called formal proofs, taking a human-generated proofs and make it completely computerized, and using one of these specialized computer languages, for example, Cork or Lean, to check it step by step and get a fully rigorous, flawless proof. So I cannot relate to this thing. I think it's just furthering the human obsession with absolute certainty. And it's a nice challenge from a logic programming point of view, but conceptually and ideologically and philosophically, I don't endorse this activity. And sometimes people confuse experimental math with this new, now very fashionable activity of
Yeah.
formalizing human-generated proofs and make it completely rigorous using computer logic.
Yeah, I mean, I agree with you that it's unnecessary, but I also think that people who think that empirical proofs are useless should at least go and do those kinds of rigorous proofs if they really think that you need to be 100% sure, because otherwise they're being hypocrites. If they think that
Right.
you can make a rigorous proof and not make it fully rigorous, and that's good enough, and it's even better than an empirical proof. I think they're being hypocrites, because if they're open to just making rigorous proofs, but not verifying it with computer logic, then they should be just as open to using empirical proofs, maybe.
That's
So
a good point.
I don't know.
I agree.
Yeah. So do you have any other opinions about the future of experimental math? How do you think it would look?
No, I'd like to, as a case study, maybe I want to interview you and
Yeah.
say about our joint project that you completely initiated. And I think it's going to be a very nice publishable paper eventually, hopefully not too eventually, soon. It's a very nice project. So tell us about first the original motivation, this
Yeah.
Turkish game, okay.
Yeah, so there's a Turkish game, okay, that I'm sure Meryem and Osman have probably heard of. It's actually like a really famous game in Turkey, and my friends and I, we always play it when we get together. But I was just wondering how like the combinatorial aspect of this game would look, or if, like what are the actual chances for a random game ending up, as a winning game, or even like can I do something that would actually help me win? So I asked Dr. Z to, go over this game in an experimental but combinatorics perspective. And we were working on that. We simulated the game and we looked at certain aspects of the game. But then we kind of moved over to like more general games and like tic-tac-toe and also just general random games. So that's what we're working on right now. But yeah, I think it's pretty cool. And actually simulating the game of okay it requires a lot of time. So yeah, we
It's very
kind of
complex. So you have to do simplified version with a smaller decks to get. But it's very interesting mathematically. And,
yeah. Yeah, so currently we're working on just like random general games and kind of just representing games as states and transitions. But maybe we can circle back to okay later once we have some sort of basis there.
yeah, and then okay will be a very interesting example to apply to. So,
Yeah. Dr. Z, have you ever played okay or anything similar to it?
no, unless I watch people play. Rumikube is similar.
Yeah, it's kind of similar. We kind of play sometimes we play Rumikube with my friends, but we mostly play okay.
Yeah, I know some of my friends do it. I watch them play, but I
Yeah.
never play.
Yeah, it's great.
Yeah.
So I
But
mean,
now, by now, thanks to you, I know the rules at least.
oh right, yeah.
Yeah.
Yeah. Yeah. Pretty cool. Um, oh, also Dr. Z, so you know how you don't believe in infinity?
Yeah.
So maybe that's like, do you think that people think that you like empirical proofs because you don't believe in infinity? They think that maybe numbers can grow very, very large, but
Yeah.
you don't seem to have the same perspective that they'll keep going on forever. So
Yeah, it's related. I know that this series is about culture. So this is part of the mathematical culture. And I know that for most people, it's so ingrained, they believe in infinity. And of course, infinity is a very useful object, and I do use it all the time. You have to, but it's just the so-called, in philosophy, it's called ontology, the existence of infinity. you can still use infinity without believing in infinity.
Yeah, like a
Infinity is that a symbol, very convenient symbol, but and the indication why you can get away in mathematics, at least in applied mathematics, without infinity, because nowadays all applied math, all computations, all applications of mathematics are done with computers, and computers are inherently finite objects. So if a
yeah.
computer can handle them, that's proof that you don't need infinity. That's a convenient way of speech. But
Right.
yeah.
Yeah, I mean, I think I believe in infinity and I still like
That's nice.
experimental math,
Some
so
of my best friends believe in
yeah.
infinity.
Yeah. But yeah. I mean,
Yeah, it's an open question. Yeah. No.
right,
To be honest, I don't say I don't believe in infinity. My famous quote is, "You don't need infinity in mathematics. You can do mathematics without
got it.
infinity, without ever
Right,
using infinity." Whether infinity exists or not exist is an interesting question, and it's still open. I cannot prove, of course, it's just a belief that there's no
right.
infinity. But we're saying you don't need infinity in mathematics. You can redo everything without think of infinity as a
Yeah.
object. Yeah.
No, I think I agree with that. And actually, like, I believe in infinity, but when people start talking about infinitesimals or ordinals, I start getting a little bit
Yeah.
annoyed because I feel like that's a little bit too far,
Yeah.
talking about numbers going on forever, but then we're talking about the number after the numbers go on
Right.
forever,
Right.
which is I
Yeah.
think it's interesting, like it's kind of like a fantasy or like a game if you want to think about it that way, but I don't think it actually exists. And I think like you can talk about things like infinitesimals as like directions or things like
Yeah.
that
That's
instead
a
of
good
actually,
way. Yeah.
yeah.
That's a good way of thinking about it.
So I'm kind of in the middle of it, I guess. So
Okay. Yeah,
yeah.
it's interesting. Interesting. Open question. Speaking of infinity, there are two kinds of infinity. That goes back to Plato, I think, Aristotle. It's the potential infinity and the actual infinity. So many great mathematicians, including Gauss, did not believe in the actual infinity. And somebody called Georg Cantor, he introduced what you alluded to, these other kinds of infinity, much bigger than the usual infinities, and an infinite number of infinities. And
Yeah.
many great mathematicians objected to it, including Gauss and Poincaré, and even today. But they still believe in the potential infinity, meaning you can always go one more. But this is a much milder infinity, the
Yeah.
potential infinity. And my some people think crackpot view that you don't even need a potential infinity. You can get away with only finitely many numbers, but you don't know
Right.
how many. But of
Yeah.
course, that's a minority view. Yeah.
Yeah, I see. I mean, even if you were to stop at a number and then wrap around,
Yeah.
technically you can keep counting infinite amount of times, right? Because keep wrapping around an infinite amount of times. So
Well, at least for you, you can do it physically.
yeah.
Eventually, you're gonna die.
Yeah, that's true. That's true.
You
Yeah.
can do it many times. That's true.
Yeah. Yeah, so I'm glad we're on the same page about experimental math. And I mean I hope to go to grad school in the future, so
Right, you
maybe I
should.
can stay on this path and try to convert everybody else as well, hopefully.
Sounds good.
Yeah,
Thank you.
yeah. So thank you, Mariam. This was a great conversation.
Thank you guys for accepting our invitation to be a part of eTalks.
Of course, this was
So
fun.
And
I
can we have the musical uh, supplement?
yes, but that will be special to you and not the
Okay.
all set of viewers. But before we end, I just want to say I learned this was my first time being introduced to experimental mathematics, sort of, and what I understood is it's not necessarily saying. You're not necessarily saying let's not do rigorous proofs, but you're saying let's not be limited with rigorous proofs in the upcoming days of math. So hopefully we everyone learned something from that. And before we end, we ask 3 questions that are nothing about the topic that you talked about. So I would like both you and both you, Nuray, and Dr. Z to answer it to your best extent. So what is your favorite book, if you have?
Oh, the favorite book? Uh, that's a good
Hmm.
one. I have uh, many favorite books. Yeah, I can tell. Okay, the,
I don't know.
if I have to say something, the Bible. Okay.
Okay. Yes.
Okay, well, if we're talking about religious books, maybe I can say the Quran because I don't have a favorite book.
Yeah.
Nice. At least you're on the same page again.
Yeah.
I didn't mention this, so I wanted to be a surprise. But another question is, what is your favorite color?
Blue, definitely.
Blue.
Blue.
Yeah,
Oh,
dark blue is what
Dark
I'm
blue.
wearing now over the shirt.
Oh, nice.
great.
And
I think I
my
have.
wife always teases me. And my wife is a neat freak, and she wants me to change my shirt every day. And I do. What happened? I bought from Amazon 6 identical shirts, blue, and I change them every day. But my wife doesn't know it, so she thinks I'm keeping the same shirt. But because I like blue so much, dark blue,
Uh,
I wear the same color shirt. So it looks like I don't change my shirt. But they're always identical twins.
oh my God.
It's very least to say you like blue. You're fond of it, I think.
Laura, you like red, maybe?
Yeah, I do. I actually have 3 favorite colors though: red, purple, and green.
Ah, a
Yeah.
good name. So we did agree here. You don't
Yeah.
like blue.
Yeah.
Nice.
So maybe I have 2 of each, and I wear red one day, green one day, and purple one day.
Ah, diversity.
But it's very interesting. You love it so much that you have multiple. Um, and the last question, is there a favorite piece of music that you have? Like artist, a genre, whichever one's easier to answer.
Well, my favorite singer is Leonard Cohen. So I like all his songs, but especially I like the song Tower, uh, Tower song. This
I
is
will.
my favorite song, but I like them all, and I have many favorites.
Yeah, I think
Yeah.
I have so many favorite genres, but um I know you keep asking what my favorite is, but I'm gonna list a few. My favorite singer right now is Elliott Smith, and I think my favorite band is Massive Attack. So those are
So
my
kind of
2.
my,
Yeah, I actually just recently bought a record. I can show you an Elliott Smith record. Wait, let me
yeah.
this.
Well,
Wow, a real record, a vinyl record. Wow.
Yeah, it's a real record. We have a record player, but it just broke, so I need to buy a new record player.
Uh-huh.
Yeah.
Traditional. That's nice.
well, thank you so much for the whole session and your answers to my questions. Thank you for your time. And thank you, our dear viewers, for joining us for this episode. We hope to see you in the future upcoming episodes.